Hello. You can see my screen, I guess. Hello.
Yes, sir.
Okay. We are talking about modulation scheme. We introduced a idea of sine triangle modulation. The objective of sine triangle modulation is to generate the pulses for the inverter. These pulses are generated in such a way that the average voltage produced in every switching period equals the intended sinusoidal voltage that must be applied across the motor terminals. So, this is some kind of a calculation, like somebody gives me a value of sine wave, some physical sine wave that must be applied at the motor terminals. Then I cannot produce that sine wave as a continuous function. So I produce sine wave in an equivalent sense using switching function. That switching function is essentially doing average, the average over a period is called switching period or TS. That period does the average, and that's how it switches the devices of the inverter, so that from a given DC voltage, the DC voltage we call it DV DC, we can if we take the average of the switched voltage, that would be equal to the sampled value of the sinusoidal voltage. Sampled value means we are sampling in every switching period Ts the sine wave, and we are assuming that the switching period is very small, or switching frequency is very large compared to the frequency of the sine wave that we are trying to produce across the motor terminals. Therefore, in that small time period, the sine wave magnitude can be conceptually thought to be constant. So this is the basic idea, that sine wave magnitude, we think that it is constant. So when it is constant, it's a constant voltage. We forget about whether sine wave how is it varying subsequently. We forget about that. We just look at that particular switching period. We only acknowledge that it can be positive voltage or negative voltage, and the switching should be such that it should be able to produce positive voltage or negative voltage, as the case may be, as the instantaneous value of that sine wave is over that switching period. So, this thing, you understand that to do this thing over the actual, that means we need to, one thing is to pre-calculate everything. So pre-calculating everything is slightly, it can be done. It is not that pre-calculation cannot be done. But when initially it started with when there were not many computers and things like that, because pre-calculation requires digital thing, where things were mostly done using analog circuits, this calculation. So they did a very intelligent thing. They developed a modulation scheme called sine triangle modulation, where they scaled the quantities. They scaled the quantities means the DC voltage was scaled as a triangular voltage. Peak of the DC voltage represented a triangular voltage. And why triangular, I had explained in the last class. Triangle has a function, kind of a sawtooth function, and sawtooth function represents time, progress of the time. If I want to represent time increasing, then I will obviously use a sawtooth function, right? The time increasing that I want to represent by a waveform, then I must represent it by a sawtooth waveform. Why sawtooth? Why it is not continuously using a ramp function? Because every we are breaking it in every switching period and recalculating it. We are not calculating one time. We are recalculating the duty ratio. We call it duty ratio. That is the on time of the switch with respect to the switching period. After every time period TS. So everything has been divided into TS part. So like that, this is the TS part. This is the TS part, and this is TS, TS, 2TS, so on and so forth, 3TS, so on and so forth. We have divided the time, and every time we are calculating. So the function is a sine, function is a sawtooth, and then that sawtooth waveform we converted, flipped it and converted into a triangular waveform. That is a convenience set, because in last class I had shown that the sawtooth waveform, if I put two consecutive sawtooth waveforms and flip it, the second sawtooth waveform, then the number of switchings will reduce. Otherwise, the number of switchings will increase, and actual number of switchings of the actual switching device you want to reduce. Unnecessarily don't want to increase, because that will mean the increase in the switching loss. So that is the philosophy of it. Any doubt, please feel free. I am trying to tell you the what I think is you are getting it, but please, if you are having any issue, then please. That is how the sawtooth waveform evolved. And basic thing is a triangle. Basic thing is a sine wave, so it must be compared with that. This is the sawtooth. This is the sawtooth. And something like that, very badly drawn, but I hope you get the idea. So 1, 2, 3, 4, 5. Let me put a sine wave here of some magnitude. So 1, 2, 2.5. I'm going to put it here. 2.5, and then this is 0. This is negative 2.5, and this is 0. So with these comparisons, first of all, here you are not getting the true feeling, but you must understand that this Fs is very greater than very greater than, here I am making a TS is the switching period, and very greater than 1 by T. 1 by T is this the period of the sinusoid that you are trying to generate. This is the T. So or rather I will say this is what is switching period. That rather I will say that TS is very less than T. T is the period of the modulating waveform. This is called carrier waveform. The green one is called carrier waveform. Green is called carrier waveform, and the red is called modulating waveform. This green waveform is VT, and the peak of the carrier, peak of the modulating waveform, which will vary, and in a drives application even T will vary, but TS won't vary. Okay, but TS is very large. Let us say 2000 times more. So it doesn't matter. T will vary, but it will not vary so much that that basic relationship is violated. TS will always remain very greater than T, right? So this is called modulating voltage. This will be VM, right? VM sine omega t. So in the last class we saw that each period duty ratio, if I define D, is coming out to be half half into 1 plus small m. That is the duty ratio it comes to be, where small m is equal to a it is equal to m sine omega t, right? And here omega is equal to 1 by t, let me call it here. So m is the called modulating signal. M is called m represents the modulating waveform, or I have already written. So m has this is done in the modulator, right? Here things are not voltage and current, they are signal levels, they are voltage, they are not there is no, they're all millivoltage, not millivolt, maybe some voltage, few voltages, but they are not. You must understand the difference between a power signal, a power quantity, and a control quantity. So this is a control quantity. This is generated through some oscillator and things like that, right? So this m sin omega t, m is defined as the ratio between Vm, capital M, by Vt. This is the ratio, which will be in the physical quantity, it will be representing Vt will represent Vdc by 2, DC bus, half of the DC bus voltage, and Vm will be representing Vac that you are trying to produce. So basically you are trying to produce V small ac is equal to V capital AC sin omega t. This is the waveform you are trying to produce. So but we are not doing comparison using the DC voltage, physical DC voltage and the physical DC voltage. We have scaled them and made them a signal level. From the actual voltage signal, we have developed a proportionality somewhere, and we have scaled it in such a way that small vm represents the sinusoidal waveform. So here the signal is Vm is equal to V capital M sin of omega t. Okay, and M is called the modulation index. M is called modulation index. M is called the modulation. M is not called modulation. Capital M is called the modulation index, right? That is capital M is called the modulation index. It is a ratio between the peak value of the AC voltage divided by the half of the DC bus voltage. So this is what I told in the last class, that we will be doing this, and so you will be generating a continuously varying switching signal. That is why it is called pulse width modulation. You can clearly see that as AC voltage is varying, the duty ratio is varying, isn't it? You can see the expression half of 1 plus m. So you can take that when let us say m is equal to let us say 0.8, which I mean the VAC peak divided by VDC by 2 is D. So D is how much? D is what kind of function? D is equal to 1 plus 0.8 sin omega t, right? So you see that as sine value is becoming as omega t in the cycle, in the switching cycle, in the TS period, when omega t is equal to, when sin omega t, let me directly write it as sin omega t is equal to 0, at that switching period, that D, let us say that D is, I am calling it as, let us say D0, just to give a name, that will be 1 plus 1 plus 0, so it will be 0.5. The duty ratio is then 0.5, right? That means duty ratio, as you know, this is the T on by Ts, that is the duty ratio. When for another switching period Ts, when sin omega t, let us say, is equal to 0.4, sin omega t is equal to 0.5. Suppose sin omega t is equal to 0.5. Then what is the D for that? D1, let us call it D1, half of 1 plus 0.5 into 0.8. So it is 1 plus 1.4 by 2. So that time the duty ratio will be 0.7. What will be the peak duty ratio? At some other TS period when sine omega t is equal to 1, then we see that d2 will be half of 1 plus 0.8 by 2, so 0.9. So this way, and similarly the lowest duty ratio you will get it as when let us say lowest duty ratio Ts when sine omega t is equal to -1, then you get d3 is equal to half of 1 minus 0.8 into 1, that is equal to 0.1. Okay, so this is the duty ratio you will get when you will be generating a negative voltage. Effectively, you are generating at that time at the motor terminal, you will be generating a negative voltage. So before the computers came, people used to do it by waveform generation, and the waveform generation and using a comparator, they will be able to find out the switch, which switch has to be turned on and for what duration, and that was continuously varying over variation of the switching periods. First period, second period, continuously they are changing. That's why the name has come pulse width modulation. Pulse width is not constant. For every, this is not a DC to DC converter. DC to DC converter under steady state, you get constant pulse width. Okay, it varies when the voltage varies. But here the voltage, you are in the beginning itself, on the steady state itself, you are trying to your duty ratio will be has to continuously modulate. Okay, because over the fundamental period by that I mean the time period t, okay, or the period of the modulating signal or period of the AC voltage that you are trying to synthesize, over that your voltage has to be synthesized, which is varying. So therefore the duty ratio has to match it, and therefore the duty, because you are using only a constant voltage VDC by 2. So the only option that you have is to vary the duty ratio, and that is what you will be doing. So it is not surprising. So it is like continuously varying duty ratio function you have to generate. That is what is given by this. This is the what is the thing that you are doing. You are producing a duty ratio just like a buck converter. If you remember buck converter, just like a buck converter, it is like a buck converter with a varying duty ratio you are producing in order to synthesize a sine wave. But you have cleverly chosen the duty ratio and the structure and the modulation in such a way that you are producing both plus voltage and minus voltage with respect to one reference, and the reference is where? The reference is the center point of the DC bus. It is not at the end of the DC bus. Your DC bus you have split into two, and this you have taken as the reference. This is VDC by 2 and this is VDC by 2. DC by 2, and you are doing a switching. You are doing a switching here, and you are measuring the voltage between this reference and this point. This is the reference. This is the your AC voltage that you want to produce here. Okay, so that is. I hope this is absolutely clear. This should be clear to you. I guess this you probably have got an idea. Right now, therefore, if I want to little bit make it clear to you, so the pulses are like this. In this, you see how are the pulses? Pulses, I'm drawing a few pulses only, so that because comparison has been done. When sine wave is high, you get high pulses. This is high, and I am talking about one of the switches, top switches. You can consider this as the pulse of the top switch, right? And here also there is a small pulse. Okay. So this is this is the top switch on pulse. Bottom switch is just a complementary. So there is no new information. So top switch is this. It also gets compared here. And you probably have an idea that the pulses are varying, pulse widths are varying, right? As the sign is positive and maximum, that zone the pulse widths are more. Okay, relatively less is the zone where sign is not this thing. This is the way the pulses. This is just a comparator. It's a comparator. This signal and this signal will be compared. This signal is VM signal, plus and minus is VT signal, and carrier waveform VT signal. So this is what the pulse of the top device is generated. I may call it Q. I may call it Q. Okay, the bottom pulse I may call it Q bar. If I want to relate it, I am talking about this. This pulse is called Q and this pulse is called Q bar. So I have this way generated the thing. You will see that the pulses will be narrowing considerably in this zone. You see that here the pulse is considerably narrowing, which is not surprising. Which is not at all surprising. Here the pulses are continuously the negative zone, the pulses will be narrow. Pulses will not be, don't say the duty ratio is negative. We have cleverly made it half DC shifted. So duty ratio for 0 voltage it is 0.5. So positive voltage it goes from 0.5 to 1 and the negative voltage is goes from 0.5 to 0. That is how the referencing has been done. The reference with respect to the voltage is considered is like this. We are not considering the voltage with respect to this reference. We are not considering the voltage with respect to this reference, but we are considering with respect to the middle, this point reference, and this is what is the AC voltage we are trying to generate. Right. Any comment?
Excuse me, sir. Excuse me, sir.
Yeah.
So how do we create that modulating waveform?
How do we create the modulating waveform? Can you suggest? Can you suggest?
Sir, using any embedded system like that?
Yes. Digitally, if you want to create, it is a sine function is there, no? That algorithm is there, right? You can. What is that called? I forget that algorithm name. Where sine cos can be created. That can be created. But I will tell you a better method. I will tell you a better method if you want to know. The method is called phase locked loop method, PLL. What is phase locked loop? That you basically sense the input voltage. Oh, okay. In this case, we have to vary the sine wave. So it is not phase locked loop here. It is the internal. What is that? In FPGA, we use that algorithm. I am forgetting that. But before that, before the digital things were there, before that it was, have you not electronic circuit, have you not read some oscillator, that Colpit oscillator and things like that? Do you remember? It's analog electronics. There are some oscillator circuits you have read?
No, sir, I
don't remember. There are some analog oscillator circuit, but analog electronics they should have been taught.
In power electronics also there were phase modulating this thing waveform, but I don't remember saying how we create that modulating waveform.
Yes, how you create the modulating waveform, I will then next class I will show a give, but you can type in Google and see that Colpit oscillator you can get. In analog electronics it used to be taught in our time. I don't know. So there are some RC circuits, the RC circuits and which oscillate in such a way that it creates, if you can dictate the frequency by that. Okay. But yes, presently all the things are digital. So it is just a code, a code for creating a variable frequency oscillator. There is another way of doing it, which is mostly people do it. I'll tell you that. And now I'm slowly remembering it. That is, you have memory. In the memory, you produce this thing. To put the lookup table. As a lookup table, you put different values of sine theta. Theta is equal to 0, theta is equal to this. So you divide the full time period, let us say, with 4096 divisions. Why I said 4096 is 4096 is equal to 2 to the power 12, something like that we do. So a memory you create, in the memory you have 2 to the power 12 or 4096 locations, and every location you put the value of the sine wave. It is sine theta values. Basically, you are producing sine theta values. You are producing theta 1, sine theta 2. Theta 2 is nothing but theta 1 plus 360 divided by 4096. Like that, you keep on you store the values here, right? Now, what has to be done is that you have to have in your code, when you think that it little carefully, whether you generate this waveform or whether you generate a high frequency waveform, always this angle in this is 36, this becomes 36 degree, right? So what happens? How do we generate? Suppose their magnitudes are all 1 for the time being. You think that all the magnitude, because otherwise this is just a scaling. Magnitude is not a big deal. So it is just a scaling. Suppose this is the waveform. There are two different sine waves. One is that these are low frequency sine wave, and these are high frequency sine wave. Suppose I know how to generate the low frequency sine. How do I know? What I do is I go and read the values after some clock period, after some period. I just go on reading the value. I keep on reading value. Okay. And this is, the clock is such that in I complete the full sine wave after after 4096 samples. I complete it. Okay. But when I have to produce a high frequency waveform, I double the clock frequency. So again, I am reading, but I am reading faster rate. I am reading faster rate. Just quickly going through it. Okay. So if I do it, then I generate the high frequency sine wave. So this is what is normally done in the TI processor, or which is mostly used for this sort of drives application. They automatically give in their ROM a lookup table which contains the sinusoidal waveform function, sinusoidal function. They give it. So what we do is, in our code, using a I first decide at what rate I should generate the what sine wave I must be generating, whether it is a 25 Hz, whether it is a 50 Hz. For example, suppose I have to generate a 25 Hz sine wave. So 25 Hz sine wave means 25 Hz is how much? 50 Hz is 20 millisecond, 25 Hz is 10 millisecond. 10 millisecond. So in 10 millisecond corresponds to my 360 degree. So since I am doing 4096 samples, so my clock frequency will be 10 millisecond divided by 4096. So this is the clock with which I go and read the table, lookup table, already pre-stored sine wave lookup table, and from that I generate the modulating signal. I don't know whether I gave an answer to your question or not.
Yes, sir, I got it. So we did similar thing in embedded systems.
We did similar things in embedded system. Okay. So,
sir, I have a doubt, sir. So this modulating signal, is it just that samples, or do we also use some sort of filter to get a smooth curve after like getting the samples from the lookup table?
No. It is just samples. Meaning that your conceptually your thing is like sample and hold type. For everything, it is sample and hold. Do you understand now? I don't know. It is like sample and hold. Lookup table is giving this kind of values. For every switching period, you are sampling the sine wave and making it constant. But you see, if there are enough samples, 4096 samples, there is hardly any variation, right? Hardly any variation. Cycle to cycle, there is hardly any variation. you have good resolution of the angle. Okay, so there is no filter required. It is do you get understand? If you look at it, it may look like it is varying a lot, because how many things I have taken? Only 5 or 10 samples for 360 degree. You think that it is 4096 samples per 360 degree. So then there is hardly any variation, right?
Yes, sir. Yes.
So there is no more filter. This kind of discrete sine table is put in the as a lookup table. We call it lookup table, which is something the values are stored in the memory, and this is in the ROM. It is not going. It is not. If you turn off the RAM, whatever is there in RAM, if you turn off power, it may get lost. But this is not so. It is the factory coded thing coming along with the IC, the TMS 320F2044, that IC with which it will be coming. So your job is to just read it. Your job is to just go get a proper clock, generate a proper clock, and at that rate you read it. Okay. Sometimes we even skip it. Okay. We even jump from when we reduce the resolution. Some in low frequency we are going minutely, angle wise minutely, and a very, very high resolution. But in the when you are generating a sine wave of higher frequency, we accordingly skip a few samples and then produce it. So the quality of the sinusoidal signal varies. In a low frequency, we need a higher resolution. Practically also, we need a higher resolution. Okay, compared to the high frequency. High frequency, these small variations are not affecting our actual performance. But in a low frequency, you need, because otherwise you will, for a long period of time, there won't be any switching. There won't be any switching. So on and so forth. But still, we don't reduce too much. Don't reduce this too much. I will tell you a little later if I get time, when I will talk about the frequency spectrum of this modulation. I will bring a little bit more clearly that what is really done. The switching frequency is never allowed to vary beyond certain value, and is never allowed to reduce beyond certain value, right? So this kind of way we maintain when we have to do high frequency sampling. So then we reduce the resolution of the sine wave. When we have when we have to do high frequency modulating signal, we reduce the resolution of our sampling waveform. Okay, modulating waveform. But when we have to do low frequency, let us say we even have to do 2 Hz waveform, 2 Hz sine wave, then you have to do lot of samples in between. Otherwise, you will be producing such a waveform which has more harmonics. Okay, so this type of thing is a good question, is a good practical question, and we make a compromise. Make a compromise means what compromise? We never go beyond a certain high frequency switching waveform, beyond the frequency, and don't reduce the frequency also too much. So we vary the sampling of the fundamental waveform, number of samples of the fundamental waveform. Okay, I will a little later, maybe a little more clarity will come. Okay, so let us first continue that somehow we have got this sine wave, but somehow it is not somehow, it is pre-stored sine wave where sine theta is there, but sine theta is not enough, because we have to produce sine theta sinusoidal waveform of different frequency. The modulating waveform has a frequency, because we are doing, you remember, we are doing V by F is our principle. So we have to change the voltage, we have to change the frequency. So as the modulating frequency is changing, logically we have to change the sine wave also. The way we generate this, it cannot be a frozen sine wave. It has to be a dynamic sine wave of different frequencies. So that requires either first strategy is to change the sampling clock, and the second strategy is to change the number of keep the sampling clock constant, but change the number of samples that you are picking in the when you are generating high frequency modulating wave, you reduce the number of samples. When you are generating low frequency modulating wave, you increase the number of samples. In this way, your waveform will be reasonably good quality at the motor terminals, and the switching periods will be more or less correct. So beyond that, smoothness is not required. Beyond this, no practical smoothness is required. Achha, so I have talked about this, but one question comes here also that I may little bit highlight, that you may see that if the modulating waveform signal magnitude increases further, suppose not this color, suppose the magnitude of the modulating signal waveform increases further, it is going beyond that, suppose it goes there, then what happens? You can qualitatively see that in this switching period there will be switching. In this switching period there will be switching. In the subsequent switching period also there will be switching. This one, second one, there will be switching. But when it is coming this switching period, next switching period, number 1, number 2, number 3, there may not be, because this level of the voltage is greater than the triangle wave, the peak of the triangle wave. So if it is gone there, what will happen? Can you tell me what will be the switching output? What will be the modulator output if the modulating signal magnitude at the, let us say, instantaneous magnitude, not all the time, but in some switching periods, if the magnitude of the modulating waveform, meaning Vm, is greater than Vt, then in that switching period, what will be the output? What will be the duty ratio? Output means what will be the duty ratio?
Sir, it will be greater than 1, sir.
It cannot be greater than 1, so it will saturate to 1. There will be, which means that there is no switching. Okay, the comparison has happened, and it is in that switching period, this voltage is the modulating signal magnitude is greater than the triangle waveform magnitude, so it has crossed. It cannot modulate further. It has lost the ability to adjust the duty ratio. By means of adjustment, it cannot produce this thing. So it will do what? It will do whatever maximum it can do. So logically speaking, as if it is requiring higher value of voltage into second, but the voltage level is limited by VDC by 2. You are not changing that. So what is the thing? That it is, we call it saturation. The duty ratio saturates, and when the duty ratio saturates means it goes beyond 1, right? And maybe in the reverse way, it tries to produce a duty ratio less than 0, right? In other words, when the modulating signal magnitude, instantaneous magnitude, is greater than the triangular magnitude, in that period, the switching duty ratio saturates. It becomes either 1 or 0, okay? Which means the quality of the output, actually we are synthesizing a sine wave. Never forget that. We are trying to synthesize the sine wave. We have logically argued that if I do this sine triangle modulation, and if I do it with a very high carrier frequency compared to the modulating signals frequency, we are likely to get a very good quality sine wave at the output. Even though this doesn't look like a sine wave, but this kind of pulse width modulated waveform is as good as a sine wave, because it has only fundamental component and no other quantity is there, no harmonic is there, and that is commonsensical, because this every switching period you are matching the voltage in some sense. Every small switching period you are matching the voltage. So what other way it can be different? It cannot be different. There cannot be any harmonics in that. Only harmonic may be high frequency harmonics. There may be switching frequency harmonics, which doesn't have much problem. We do not have much problem with switching frequency harmonics, because the motor's inductance, the leakage inductance of the machine, will filter the current of it, current due to it. So I'll later give a much better explanation, but you develop your common sense. So the common sense is saying that this time I have failed. The modulator has failed. Modulator has done the maximum it can do. It has done. It can only produce a duty ratio 1 by definition duty ratio cannot be greater than 1. So it has produced a duty ratio 1, and that's what. So what is happening is, due to this, there will be distortion. Distortion in what sense? Distortion means by looking you cannot see much distortion. You can see much distortion. You will see that the waveform is not switching enough number of times. It is expected that every switching period there will be switching, but here you will see when it saturates, in that period there is no switching. So in one sense you can feel that it is distortion. In another sense you can feel that there is less complicated waveform. But this less complicated switching waveform is a problem, because it is then producing harmonics in the low frequency harmonics. High frequency harmonics we are always tolerating. High frequency harmonics is not a problem, because it will be filtered by the leakage inductance of the machine. Because at high frequency the leakage inductance is also impedance wise multiplied by that frequency. So it has a better attenuation ability, but here filtering ability. But here the low frequency harmonics will be coming across the machine terminal, and with low frequency harmonics we know that the induction machine torque, speed characteristics will be very much affected. It will produce pulsating torque. It will have lot of issues. It will have lot of unnecessary current in the machine. Machine will be heated and all sorts of things. So that is not as such allowed, and we must choose our DC voltage accordingly. We cannot afford to choose a very low value of DC voltage. That is what I am trying to emphasize here, that we cannot afford to choose this one, because then it will be going into over modulation. This is called over modulation. Over modulation. Over modulation. It is called in the machine has entered or into over modulation zone. So over modulation zone is implying that the voltage that is applied at the motor terminal is such that the generated voltage waveform from the inverter not only contains some fundamental, but it also contains some harmonics. Okay, so this over modulation, when it goes to the extreme, what is the extreme case? That over the period it continuously gives duty ratio 1. Okay, one case duty ratio 1, another case duty ratio 0. So that is what is suppose the voltage level is very high, the intended voltage level is very high, then there will be only one switching in the period, not one switching, two switching, or one switching, one high and one low in a period T, not TS, from TS to T. So then the signal will look like over complete, not this color, let me do a different color. It will be going complete high here and complete low here, complete low. Only one switching, one turn on and one turn off in the entire period, right? So that is when you are producing a square waveform. Instead of sine waveform, the actual voltage that you are giving to the motor terminal is plus VDC by 2 and minus VDC by 2. Plus VDC by 2 for a period of T by 2, capital T by 2, and minus VDC by 2 for a period of minus for a period of T by 2, right? So this is what is called square wave operation. Square wave operation. So you have understood that to produce sinusoidal waveform, the peak of the sine wave must not cross the value of VDC by 2. That is one. That is what the limitation. As long as that is happening, you are able to get. So what is the constant for modulation zone? Modulation. This is the peak of the sine wave. Modulation. Peak of the sine wave is less than equal to VDC by 2. Okay. And when this is VAC, peak of the sine wave. Actual waveform is VAC is equal to capital VAC sine of omega t, right? So beyond that, it is over modulation. That means your VAC is greater than VDC by 2, if you are intending that, you are entering over modulation. Over modulation zone. Implication is produces lower order or order harmonics. Harmonics. It is only produces fundamental plus higher order harmonics. Higher doesn't matter too much. Higher order harmonics. That is the thing. Here, along with that higher order harmonics, that is there. But to note higher, that will always be that. The number of switchings that are happening will produce higher order harmonics. That is okay. Higher order harmonics as well. Harmonics. That will be there. Okay. But extreme case, this over modulation extreme is saying that you will be producing a square waveform. This is a square waveform. Square. That means you are producing VDC by 2 for a period of T by 2, and you are producing minus VDC by 2 for a period of T by 2. That is the cycle. That is the total period T. So this is what is one of the square wave mode of operation. Square wave mode of operation. And when you are producing square wave mode, you are essentially not generating any higher order harmonic switching frequency. Higher order harmonics means switching frequency harmonic. You are not generating any switching frequency harmonic because there is no switching. There is no switching. It is continuously duty ratio is 1. There is no switching. So, but you are generating all sorts of harmonics, all sorts, because it's a square wave. So you are generating fundamental. It so happens the fundamental magnitude is very high. Fundamental is highest in this case. Fundamental, more fundamental. In fact, the maximum fundamental is happening here. Fundamental is maximum here. Fundamental magnitude maximum, but with that all low order harmonics. Right. So you can quickly check what will be the difference. Let us say it has reached VAC is equal to VDC by 2. So what is the sine wave that it is producing then? I will say that VDC by 2 sine omega t. And here what will be the sine wave in the square wave mode? It is in this mode. It is VDC by 2 sine wave. And what is that in the square wave mode? Fundamental component, because it's a square. You remember the Fourier formula. Fourier formula says that Fourier series first fundamental is 4 VDC by 2 n pi, n is equal to 1, 4 VDC by 2 by pi, right? This is the thing. So what is the how much it is greater? It is greater by 4 by pi 1t. Okay, so that is the difference. Difference is that when you are producing only fundamental component and not producing any lower frequency component at the motor terminal, you will be limited by the amount of fundamental that it can produce, because if the amount of fundamental will be such that its peak is equal to VDC by 2. So it can only produce a fundamental which is VDC by 2, because this is exactly at that point the duty ratio is equal to 1. If you intend to get some more thing, number fundamental, you have to give up that condition that you don't want harmonics to be produced at the motor terminal. So so the fundamental will increase at the cost of low frequency harmonics that will be produced at the motor terminal. But if you say that I don't care about the harmonics, for example, I want to know how much maximum voltage I can produce. So then it completely goes without switching within the period. It has only one switching, one high and one low over the period T. There is no switching in between, and you generate a waveform which is a square waveform. A square waveform plus VDC by 2 and minus VDC by 2. And therefore the fundamental from our Fourier series, we already know it's a very easy formula to remember, 4 VDC by n pi for a square. N is the harmonic number. So n here is equal to 1. So therefore it is 4 VDC by 2 divided by pi. So the coefficient is 4 by pi, and 4 by pi is greater than 1. You can clearly see is greater than 1. So you will be getting slightly higher fundamental component. However, you will be losing on the harmonic front, and the losing of the harmonic front affects whom? Affects the machine. Affects the machine in what means? It affects the machine by increasing its harmonic current. The current waveform is then no more looks like a sinusoid. It looks very distorted. Very distorted current means it will be with current component will have all the third harmonic, fifth harmonic, seventh harmonic components, and the seventh harmonic, fifth harmonic components produce pulsating torques, and the machine then behaves in a bad manner. And its life also decreases, right? So all modern day inverters means inverters which are rather using modern day devices, and modern day devices, by that I mean devices such as IGBT, MOSFET. Nowadays this is silicon carbide, a new device has come. Initially this is a silicon device. Silicon is the base. Now a new material has come that is called silicon carbide MOSFET. They are used in this in the inverter applications, and mostly they are used in the industrial kind of applications. Where the power rating may not go beyond 500 kilowatt kind of thing. But there are some high power applications like traction. And traction, the point is that they use a machine. The machine part, they make it very robust, and the traction part is very high power requirement, 4 megawatt kind of thing. And in the 4 megawatt kind of thing, if you want to use higher switching frequency, okay, you will be causing lot of loss in the power converter, and the power converter design will be very ungainly, and it will not be possible to manage it. Efficiency will be very low, and so on and so forth. So traction, this thing, because of this is a high voltage and high current system. The devices are such that it doesn't switch at high frequency. Okay, there are still silicon devices, but don't switch at greater than 500 hertz. Whereas this is industrial type, is the switching frequency is greater than 10 kilohertz, greater than equal to, or I will say 5 kilohertz. So almost 1:10, 1:10 factor is there. So think about it. In the traction type, since we are unable to utilize a device at higher switching frequency, we are unable to use, because the voltage will be, let us say DC bus voltage will be 2500 volt. In this case, DC bus voltage VDC is equal to about 600 volt. In this case, VDC is equal to 2500 volt. In fact, in this case, the I current is equal to maybe 2000 ampere. So such high voltage and high current, when the switching device has to go transitioning between on and off, this thing multiple times, every time it goes through that transition, there is a loss. Okay, because we are not able to operate in such a manner that voltage and current simultaneously don't appear across the switch. That is the condition for ideal switch, that voltage and current across it will not simultaneously appear. But it is not possible. For a small time duration it appears, and in these devices, because of the physics limitation, the semiconductor physics limitation, this time is not so small. It becomes in microsecond. Whereas low voltage devices, it goes into some kind of nanosecond. So there is also difference. So these sort of differences produce a situation where the device's switching frequency has to be limited. Okay, I have given a number 500 Hz, and that 500 Hz, but the machine has to operate at a low volt machine at low speed as well. And at the low speed, you understand that we have to generate a modulating signal that is at relatively low frequency. And the relatively low frequency modulating signal will require a good amount of switching, good number of switchings, because otherwise the harmonic component becomes very much dominant, right? So these are the issues which we have to take into consideration and understand that in the traction drive there exists a square wave mode of operation. Square wave mode of operation. Square wave mode of operation exists in this kind of devices, so that the converter power loss is not so high due to the losses in the devices at higher switching frequency when it has to deal with high voltage and high current, because the application itself requires a lot of tractive effort. So therefore the machine and the system is at megawatt level, 4 megawatt, 5 megawatt, things like that. And 4 megawatt, 5 megawatt thing, it requires such kind of semiconductor devices which has higher switching time. We call it T on and T off are larger compared to this low voltage devices. This 600 volt application requires 1200 volt IGBT, and this requires 4.5 kV IGBT. This requires 4.5 kV IGBT, and this 4.5 kV IGBT, not even 500 Hz, it will not go beyond 250 Hz switching frequency. The switching frequency don't switch at greater than 250 Hz. That is the issue, and keeping that in mind, we have to learn how the inverter operates in the most simplest way, that is the square wave way. And what happens to line voltage? What happens to line to neutral voltage? What happens to between two neutral points? One neutral point is the neutral point of the machine, and another neutral point is the neutral point of the inverter. The neutral point of the inverter is the center point of the DC bus. So we have to learn now how the machine will operate in square wave mode. Okay, so that I will take in the next class, that how the machine would operate in the square wave mode. If you have one or two small questions, please feel free. Anything you want to ask?
So the omega synchronous and the VS is fed to the modulator via the feedback path. So when is the case of overmodulation arises?
Where is the case of overmodulation arises? So overmodulation case of arises is, let us you see that one interesting thing. You have, suppose the DC voltage is 600 volt, right? DC voltage is 600 volt. What is the AC voltage you can produce using this DC voltage? If you don't do overmodulation, you can produce a DC voltage of 600 by 2 is the sine wave voltage. You got it? Yes or no? 600 by 2 is the magnitude of the sine wave you can produce, right?
Yes.
Divided by 1 by root 2 is the RMS value. How much is it? Where is my calculator? Can you calculate? I will show you that. 300 divided by root 2. 300 divided by root over of 2. So it is only producing this is only producing 212 phase voltage, right? Into root 3. Line to line voltage will be 212 into root 3. So why I am saying the machine rating is, I am trying to compare. So into root 3. So it is producing 367 volt, right? However, in the standard machine, you will get is 415 volt machine. Okay, so machine is underutilized. Look how much difficult it is. From a 415 volt supply system, when you are generating DC bus by doing a rectification, in fact, you don't go to 600 volt. Let me assume that you are going to 600 volt because you remember the function into cos alpha function. So you will get into a voltage of, let us say, you cannot go beyond 600 volt DC. You cannot get, because you are doing diode rectification. You cannot get beyond that. Okay. In fact, how much you can get? 415 into 586. You can get only up to 586 volt, right? But if you, I'm simplifying it, I'm just assuming that it is 600, right? Then from the 600 volt through modulation scheme, you can generate an AC voltage only about 367 volt. But the machine is designed for 415 volt. So you are underutilizing the machine. You are not able to apply 367 volt to the machine. Machine is underfluxed because that is what you are able to do. So there is a natural tendency somehow to increase the voltage and go to the 415 volt. So when you are multiplying by another factor 4 by pi, which is an over-modulation maximum zone, so how much it is that? 4 divided by 5. So that is how much? 1.27. So 27% extra voltage you are getting in the fundamental sense is a big temptation. Is a big temptation. So you would have got 367 into this. So you would have got 467 volts. You would have got this voltage. So that is the temptation people have to fully utilize. There is a language called full utilization of the DC bus. Full utilization of the DC bus is saying that 600 volt DC bus you can, in fact, not 400. Did I do? 367 into 1.27. Yes, 467. Right. So you are full utilization of the DC bus is saying that you can generate much higher voltage, fundamental voltage. This is fundamental voltage. Must understand that if you do over modulation or square wave operation. Okay.
But then if we give square wave to the induction machine, then its characteristics will also be affected and hence the feedback path also.
No, machine is AC, does require AC. No, fundamentally you are giving AC. A square wave is also AC, but it characteristics means I told you now that it will be performing in a with a lot of pulsating torque, is because this current is not good. I can analyze that in some class. What will happen if the machine is not given a sinusoidal waveform but a square waveform? But you cannot forget the fact that in the square waveform also a sinusoidal waveform is hidden, and that is the maximum quantity. No, that is the maximum quantity. So it is not that we are not giving a sinusoid, but along with the sinusoid we are giving a lot of unwanted waveforms. That is the third harmonic waveform, that is the fifth harmonic waveform. Third harmonic will not be there, but third harmonic gets cancelled in line to line. So fifth harmonic, seventh harmonic, these things are there. So they create pulsating torque, they create many problems in the machine. But people are crazy, you know. People, there are a lot of profit motives also work. Not all the time you can afford to do the best thing that is possible. Engineering is very much compromised by a lot of profit things, etc. So in the traction drive which carries this huge huge loads on the traction drive, most of the time it is working on the square wave mode. Most of the time, once it reaches full speed, it goes into square wave mode. It operates in the square wave mode. Yes, the machine becomes bad after 3 years, but they have probably calculated the machine loss is they can replace the machine after 3-4 years. That may be less expensive than designing a very expensive inverter, and almost technical challenge is there to design such an inverter, because you are not getting an appropriate switching device. Appropriate switching device is not there at that high voltage. 4.5 kV switching device is not there, which has good switching time. One device becomes good and bad as a switching device based on the transitions. How much transition it encounters, how much loss it encounters during transition from on to off or off to on. So these 4.5 kV IGBTs, which are required for such high voltage system, is not good. You will get the efficiency of 80%. So 80% efficiency means 20% is loss. And what is the electricity cost of 20%? They have probably calculated the the machine, poor machine, let the poor machine die after 3-4 years. But the electricity, still there will be benefit in using the inverter at a low frequency mode, very low frequency or square wave mode. So this is the these are the practical issues that come in. Not all the time the designs are based on what is best possible. Now there are other efforts going on that you see that the essential problem is that the device is 4.5 kb device IGBT. If we use, then it will be. Then there are new topologies coming in, that is called multi-level converter. So that means we are dividing the thing into small DC buses. Okay, and then we can use low voltage devices. Okay, so but that is a complicated system. Here is this simple pulsing, lot of other things are there. The maintenance people will complain, other people will complain, and so many things are there. So whatever we learn in the classroom is only one part of the story. The actual choice is made in a much more complicated manner, where many other considerations are there. Did I answer it? Give a reasonable answer? Hello.
Yes, sir. Thank you.
That's what. Okay, then I will close here. Next class we will talk about square wave operation.